Hey everybody, I'm back with another kind of challenging proof that really is showing you how to do this from sort of beginning to end without a lot of prompts or scaffolding along the way. These are sort of the most difficult type, but if you can figure out these, then everything else should be a little bit easier. This is a proof about the diagonals of a kite. So prove that the diagonals of a kite are perpendicular. What is a kite? So a kite is a shape that has consecutive or adjacent next to each other sides that are the same length, like this. Let's go fly a kite, kind of a kite. So these are the same, and these ones that are next to each other are the same. Let's call that K, L, M, off my page here, M and N. Okay, I'm trying to show that if I draw diagonals, this diagonal here and that diagonal there will be perpendicular. All right, so thinking through the logic of this, wow, how do I do it? I think what I'm going to do is I'm going to draw a line down the middle and show that these two triangles are the same, and then I'm going to draw conclusions about these angles down here and these angles up here, so that then if I draw another diagonal, I can make a claim about these two smaller triangles, and once I've got these two smaller triangles congruent, I can say these angles add up to 180 and are the same, and that's going to be 90 degrees and perpendicular. So that's like my basic strategy. It's really helpful to work sometimes from the bottom up. I know that if I can say that each of these angles are 90, I can say that they're right angles, I can say that they're perpendicular. So that's my goal, is to get this little angle 1 and that little angle 2 in my diagonals to be the same measure. All right, so I'm going to just start with the given that quad K, L, M, N is a kite, okay? And that's a given. All right, that's our starting point. And I would say step 2 then is just going to be that I'm going to draw, I'll point out that these sides are the same length. So I'll say KL, that's not very good, KL is congruent to LM. And that's a definition of a kite. And then I've also got MN and NK. MN is congruent to NK. And that's the same thing. I'm just saving myself some time writing. So then step 4 is, once I've got these sides, that's 2 of the 3 sides of this triangle, but I need that third side, so I'm going to draw this line. Quite often you have to draw extra lines or create extra angles. So I'm going to say draw, can't write and think and spell at the same time, draw LN, and that's just, we'll call that an auxiliary line postulate that allows me to draw a line between, or a segment between, any 2 points. Step 5 is going to be then, oh look, this is congruent to itself, all right? So LN is congruent to NL, and that's just the reflexive property postulate, okay? And if that's the case, then I've got 2 congruent triangles. Why am I doing that? Because I want to build up angles that are the same and then show that the diagonals have angles down here that are the same. So I'm going to say triangle KMN is congruent to triangle, LMN. Careful, you always want to check your work. LMN, and that's LKN, triangle LKN. And that's because of side, side, side. The letters should go in the same order from the same relative parts, same corresponding parts. So now this is where I'm going to start to say, all right, I'm going to try to prove that these diagonals are perpendicular. So I need to draw this other diagonal, okay, KM. So draw KM, and I'm going to say same thing as before, auxiliary line postulate. And then step 8, I'm going to say that, okay, now that I've got these smaller triangles, I'm going to say also at, let's call that point Q. All right, that's point Q right there. okay? So I am going to then say that angle 1 up here and angle 2 right there, angle 1 is congruent to angle 2, because in these bigger triangles, these are corresponding angles. I could have done it, or maybe should have done it before I drew that line just for clarity, but when I fold over my first big triangle, those are corresponding angles. So CP, CTC, and then I'm going to say, well, if that's true, then LQ in step 9, LQ is congruent to itself, QL, and that's reflexive. And so I can mark that right here. I've seen in some of our printing material, they'll use an X there, so I'll distinguish that from the 3 marks down here. That means that this little triangle up here is congruent to that triangle there because of side, angle, side, matching up with side, angle, side. So that's my step 10. Triangle KLQ is congruent to triangle MLQ because of side, angle, side. All right? So it's getting closer and closer. I can then say angle 3 down here and angle 4 of these smaller triangles have to be corresponding and therefore congruent. So I can say in step 11, angle 3 is congruent to angle 4 because of CP, CTC. All right, I've constructed this step by step by proving those triangles. Those are the parts now. In step 12, I'm going to say that angle 3 and angle 4 are a linear pair, okay? That's the definition of a linear pair. I know that they are because I've looked with my eyes and I've seen that there's a line and a line coming off of that line. That makes a linear pair. So that means step 13 is going to be that angle 3 plus angle 4 equal 180. That's the linear pair theorem. We proved that in class. Okay, you can see where this is going. Just pause and finish it yourself. Well, if that's true, angle 3 plus angle 3 equals 180. Okay, how can I do that? Well, that's just a substitution. Things that are equal can be subbed in. And then step 15 is going to be 2 angle 3's equal 180. That's just doing some math and gathering up like terms, combining like terms. You could get away with doing a little bit of combo step here. I don't think you'd lose a lot of points if you sort of saved a few steps. You could just say solve. Anyway, angle 3 then equals 90. That's the division postulate of equality. And if angle 3 equals 90, then angle 3 is a right angle. And that's definition of right angle. And this is where you could probably just jump to the chase, that if you've got 90 degrees there, you can say that KM is perpendicular to LN, and that is definition of perpendicular, that they meet at right angles, okay? And that is what we were trying to prove, perpendicular. I want to get that all out so I can put an exclamation. All right, so look at that, 18 steps, but when you break it all down, there's a logic and a flow to it that's kind of beautiful. All right, so hopefully that helps a little bit. Good luck, everyone.